In this lecture, I want to talk about two issues that involve scope. One is recursive definitions, and the other one is dynamic scope. What's a recursive definition? If you look at line 4, it's not obvious what this means. Am I defining this variable in terms of itself? Or am I defining it in terms of the outer definition of x? What's going on here? In fact, if you run this program in GCC, you'll get some warnings saying that you have used a variable before it's initialized. And that warning gives you some hint about what C is doing here. C is saying that this occurrence of x on the right-hand side of line 4 is referring to this declaration on the left-hand side. However, the occurrence on the right-hand side is being used before the left-hand side has actually been initialized. And that's what's giving us the error. This is an undefined program in C. It could do anything. Last time I ran it, it gave me 1 because the initial value of x happened to be 0. 0 plus 1 is 1, and so it printed out 1. It's unlikely to give you 11 in any C program. Java converts this warning about uninitialized variables to a proper error. Java will firmly refuse to run such a program, so we don't know what it would do. In Scala, they decided to allow these kind of recursive definitions, but they are defined in Scala, unlike C. Every field and variable in Scala is initialized to 0 before I run the right-hand side of any initializer. And therefore, x is defined here to be 0. It's not a coincidence. And this expression is well formed. It actually gives me the output 1. If you disassemble the class that Scala creates for this line of code, you can see what's going on. I have a final int x, which Java initializes to 0, and the use of x here is actually just a method call getting the value of the field. So when I initialize, here's the actual initialization code marked public here. First, we get the value of x. It's going to be 0 initially, then we get 1. We add them together, we put it in. So this is perfectly well defined in Scala. Scala has this kind of declaration in order to allow you to define recursive structures. And this one is not very interesting, but if you think about a recursive list-like structure where the values are sort of updating over time, and I get an infinite supply of values from this list-like thing, that may be interesting. Let's try to code it up. It would look something like this. I have a list defined in terms of itself. Now, unfortunately, this doesn't immediately work. And in fact, if you just type this in, you're going to get a null pointer exception. Why is that? Well, the variable xs is initialized to 0, which for object types is null. And therefore, this is actually a console which has 1 and null. And note that null is not nil. So when this goes to print, it will hit a null at the end, not a nil. And it will be unable to print it, gives us a null pointer exception. Sad and bad. We can try and code up our own list class where we have our case class here for the head and the tail. And then we can create an instance of that. The great thing is now we can actually print out the object because we're not invoking this nil-like thing. Scala will happily print out the null here. But we haven't really managed to get a recursive structure the way we like. But what if we were to thunk this reference to SS? That is, we're to delay the computation, not get the value now, but get the value when we need it. We can do something like that using function types. So here, I'm going to define my list console to take the head element. And instead of taking the tail directly, I'm going to take a function that when invoked will give me the tail. I can then use that thing to define a recursive value. So here, my list of t's is defined in terms of itself. And what's interesting about this is that I can invoke the tail on this guy arbitrarily. I can get 1 tail, 2 tail, 3 tail, 4 tail, 25 tails. This thing is an infinite structure because it's looped back on itself. For example, if I go through the tail twice and get to the head, I'm just get 1. The head is always 1, no matter how many tails I go through. This is exactly what Scala streams do. They're built into the language, and there's a special constructor for them, which is hash : The hash : constructor is non-strict in its right-hand side. It thunks that right-hand side. And so what that means is that we can define the ones stream here directly in terms of itself. The stream cons constructor is strict in its left-hand argument. That means we have always one value sitting there waiting for us, but the rest of those arguments are not known until they're actually used. And this is reflected when Scala prints out the value. It will show us one value in that stream, and then for the rest, it's like, I don't know, could be anything. What we can do is take several elements from a stream, and if we do that, we just get a shorter stream. So it's not very interesting to look at. But if I have a finite stream, I can invoke the toList function on it, and that will give me out the list of numbers. If you take this infinite stream and invoke toList on it directly, we'll get an infinite recursion. A list of all ones is all fine and dandy, but can we do something interesting with this kind of recursive definition? You betcha. Here's a function f that takes an integer and returns a stream. What does that stream do? Well, it's the variable x in front of the result of calling the stream on x plus 1. So this is actually an increasing stream. What I'm going to do is print out the value of x right before I actually create the con cell for the stream. You can see that if I use the function f to build a stream, we immediately create the con cell with 10. But note that we haven't done any further recursive calls. Only when I go to use those values will I actually take them out of the stream. And note that we've already computed 10, or 10 has already been added in, and we won't do it again. So when we want 4 elements, we'll get out 10, 11, 12, 13. But note that we only have to evaluate the stream on the remaining elements that have not already been evaluated. So streams are smarter than the kind of recursive functions I was talking about earlier. They are truly lazy in the sense that once they compute an element at a given position of the stream once, they will never compute that element again. And you can see that if I go to take more elements out, well, I've already got the first 4, but I haven't gotten the 5th and the 6th, and so those need to be computed. But we'll only do it once. Lazy evaluation is fascinating, and there are languages that are built entirely around this concept of doing lazy evaluation. One such language is Haskell, named for Haskell Curry. That was his first name, Haskell. What a great name. Anyway, Haskell Curry was one of the founders of functional programming back before there were computers. And that language uses lazy evaluation throughout. But for now, we're going to leave the concept of recursive definitions and lazy evaluation and move on to talk about dynamic scope. The basic question we're going to look at can be understood by looking at this example. So here I have a variable x on line 1 being set to 10. Then I have a function foo, which updates x to 20. My function bar declares a local variable x at 30 and then runs foo. At the top level, I'm going to run bar, and then the question is, what's x? Okay, so depending upon your model of languages, you might immediately have an answer. The basic question here is, which x do I mean on line 3? Do I mean the x declared on line 1 or the x declared on line 6? They're both reasonable from a given interpretation. There's two approaches to this problem. The first is called static scope, and the second is dynamic scope. In static scope, the identifiers are bound to the closest occurrence of an enclosing block of the program code. This gives us a nice property, which is that we can rename identifiers as long as we rename them in the chunk of code that they appear in. This is known as lexical scope as well. In dynamic scope, identifiers are bound to the occurrence of the closest function call or activation record. Dynamically scoped languages do not enjoy the static scoping property, so renaming variables locally might actually break the entirety of your code. And that's why static scope in general is more popular. Let's think about a function here where I have some non-local reference, z. The question is, where does this come from? We have two local variables here, x and y, but z is non-local. In dynamic scope, the non-locals are resolved dynamically at runtime. In static scope, these non-locals are resolved by the compiler. Because static scoping is more common, it's probably more familiar to you, and that's what you expect this program to do. So here on line 3, when I update x, I'm updating the global value of x, not this local variable, and therefore I expect this thing to print out 20 because foo here has actually updated the value of the global variable. Under dynamic scope, however, you may not get that result. So the bash scripting language will actually give you the other result here because it uses dynamic scope. To understand this, you need to understand the dynamic chain of events. First, we declare x on line 1. Then we process the two function declarations. Then we run bar. Bar creates a new declaration of x on line 6, then invokes foo. When we get to foo, we're referring to an x that is the most recently declared x. That is the one we just declared in bar. And therefore, this updates the value of x in bar, not the global variable declared on line 1. And therefore, this will just print out 10. C is statically scoped and therefore prints 20 for this program, just like Scala. But C also has macro expansion. And macros are expanded in place. And you can see here, if you just take this definition, x is 20, and you expand it out here on line 5, well, you're going to be accessing the x declared on line 4. And thus macro expansion has the flavor of dynamic scoping. Scope is interesting in Python. Python prints 20 for this program, and therefore it's doing the right thing. One thing that's interesting about Python, however, is that in order to assign a non-local variable, you actually need to put a non-local declaration into your function definition. So this allows me to update the non-local variable here declared in main. Python has a separate syntax for updating global variables, which are declared at top level. The global scope is something that can change dynamically. So it's possible for me to write a function here, useX, which will print x. And if I just invoke that function directly, I'll get an exception from the runtime system saying, I'm sorry, x is not defined. Later on, however, I can run a function called defx, which declares a global variable x. And after that, if I try to use x again, well, it'll work just fine. And so you can see that this use of global variables in Python is very different from what you would get in something like C, where the global variables all need to be declared before the program runs. Dynamic scoping is often thought of as kind of a bug. Many languages have started off doing dynamic scoping and then later added static scoping. That happened in Lisp. Old versions of Lisp will print 10 for this code, whereas newer versions will print 20. scheme is a fixed version and therefore does print 20. When Perl first added local variables, it got this wrong, and they later added my variables to fix this. The old syntax for local is still there, and then the new syntax for my. One of the style rules for Perl is to never use a local declaration, always use a my declaration. You might wonder why these languages started off with dynamic scope in the first place. And it has to do with a particular model of execution. So if you think about the variables that are currently in play as being sort of in a hash table, and what I'm going to do when I look up a variable is simply a hash table lookup, then you think about, well, how am I going to implement this idea of a function call and a scope of a variable? Well, the way that it's tempting to do in a simple implementation is to simply have a stack of hash tables. So when I go to look for a variable, I look it up in the first hash table. If it's not there, I go to the second hash table, and so on and so forth. This kind of dynamic lookup is easy to implement in an interpreter, and that's why it's kind of common for interpreted languages to start off with this particular approach.